So the next presentation is given by Dr. Alexander Sakharov from Kazan University in Russia. He's presenting a talk about generalization of mixed mode crack behavior on the basis of nonlinear fracture resistance parameters. So please.
Thank you, Mr. Chairman. Dear colleagues, ladies and gentlemen, my name is Alexander Zakharov. I'm a senior researcher from Kazan Scientific Center of Russian Academy of Sciences. And let me introduce you, my colleagues. We are Professor Shlianikov, Dr. Tumanov, and Dr. Anastasia Tartygasheva. So the title of my talk is Generalization of Mixed Mode Crack Behavior on the Basis of Nonlinear Fracture Resistance Parameters. The outline of my talk is following. First of all, some words about motivation. When we speak about subject of study and material properties. After that, I will talk about nonlinear fracture resistance parameters, which we used for mixed mode loading conditions characterization. And then I will talk about our finite element modeling and results of our numerical calculations, and finally will be conclusions. So mixed mode fracture is a very actual problem because in mixed mode crack growth is typical for most of structural elements subjected to cyclic complex stress state in operation. So it is well known that the mixed mode conditions appear when the direction of applied loadings doesn't coincide with orthogonal K1, K2, K3 space. And mixed mode fracture in both brittle and ductile materials has been studied in literature, and a wide range of experiments have been performed and several fracture models proposed. And for our research group, the mixed mode crack growth is one of the main scientific interests. And in this figure, you can see some our papers concerning this problem. And the main aim of this study is estimation of coupling mixed mode loading and elastic plastic material properties effects on the behavior of such nonlinear fracture resistance parameters as the stress triaxiality, J integral, and the plastic stress intensity factor. So the subject of our study are two types of cruciform specimens subjected to biaxial mixed mode loading. One of them is a flat specimen, and another cruciform specimen with finite working area. And another subject is a compact tension shear specimen subjected to uniaxial mixed mode loading. Different degrees of mixed modes can be realized by combination of the following parameters, where initial crack angle with respect to loading conditions, loading direction, nominal stress level, and in the case of biaxial loading is biaxial stress ratio. In this study, in order to characterize mixed mode conditions, we used plastic mode mixity parameter in the following form. As I said, one of the main aim of this study is evaluation of effects of elastic plastic material properties. So in this way, we considered four types of materials, two types of construction steels, and aluminum alloy and titanium alloy. So the main mechanical properties for each material were obtained by standard tensile tests, and stress strain curves for each material were described by well-known Ramberg-Osgood equation. So these mechanical properties is a basis of our finite element modeling. Now I would like to talk about nonlinear fracture resistance parameters, which we analyzed in this study. So first of them is a stress triaxiality parameter. So according to well-known Professor Hutchinson, is a very convenient parameter for describing in-plane and out-of-plane constraint effects in cracked bodies. In this study, we proposed to use the plastic stress intensity factor for mixed mode crack characterization. So the plastic stress intensity factor can be expressed directly through the elastic stress intensity factor by using well-known Rice J integral. And in order to calculate plastic strength intensity factor, you need to know values of governing parameter of elastic plastic stress field around the crack tip, IN factor. So in this study, we used a numerical procedure for calculation of EN integral proposed by our colleagues Professor Shlenikov and Dr. Tumanov. And the last nonlinear fracture resistant parameters, well known J integral. Some days ago, we had a great opportunity to be on the lecture of Professor James Rice. In this study, for calculation of J integral, we used algorithm of numerical determination proposed by Lee and Leibowitz. In this figure, you can see the finite element models of considered test specimens. In the case of a compact tension specimen and a flat cruciform specimen, we used a plane strain 8-node isoparametric elements. And in the case of cruciform specimen with finite working area, we used three-dimensional 20 nodes isoparametric elements. In this figure, you can see parameters and loading conditions for all considered specimens. As I mentioned before, the different degrees of mode mixity can be realized by combination of initial crack angle, stress level, and biaxial stress ratio. In these tables, you can see the matrix of our numerical calculations. And I would like to introduce you our results. In this figure, you can see distributions of IN integral as a function of mixed modes and elastic plastic properties of considered materials. I would like to pay attention that IN integral is almost unchanged for all considered test specimens when the mode mixity MP is lower than 0.6, and in the case of mode mixity when MP is higher than 0.6, it is observed a significant effect of elastic plastic material properties. And this region, when mode mixity MP varied from 0.6 up to unity, may be regarded as a transition area of between two dominant mechanisms. In this figure, you can see the IN integral distribution as a function of specimen geometry. Again, I would like to pay your attention that influence of specimen geometry, constraint effect, is realized when the MP is higher than 0.6. And then in the next figure, you can see the distribution of stress triaxiality parameter. Again, significant effect of elastic plastic material properties is observed when mixed mode mixity parameter MP is higher than 0.75. In this figure, you can see the distributions of stress triaxiality parameter as a function of specimen geometry. And in contrary to the IM distribution and stress triaxiality parameter, the G integral, the elastic plastic material properties effect on the distribution of G integral is observed in the full range of mixed modes from pure mode 2 up to pure mode 1. Also, it should be noted that G integral at pure mode 1 is less than G integral at pure mode 2. So it can be explained in terms of plastic zone that develops directly ahead of a crack tip in a large scale under mixed mode loading with respect to pure mode 1 condition. Again, you can see distributions of G integral as a function of specimen geometry. You can see that G integral is very sensitive to the constraint effects. In this figure, you can see results of calculation of plastic stress intensity factor for each considered test specimens. Again, I would like to pay your attention that in a range of mixed modes when MP is lower than 0.6, the plastic stress intensity factor is almost unchanged. And of course, a significant effect of elastic plastic material properties on the plastic stress intensity factor distributions is observed in the full range of mixed mode loading. In the next figure, you can see the plastic stress intensity factor distributions as a function of both mode mixity parameter and elastic plastic material properties, which described by strain hardening exponent. And these results demonstrate that in plane strain and full three-dimensional problems, the plastic stress intensity factor can be used as a general one-term parameter to characterize the fracture resistance for a variety of specimen geometries and different mixed mode loading conditions. And now I have to conclude. So cruciform specimens of two configurations and compact tension shear specimens subjected to mixed mode loading were used to study the crack tip nonlinear fracture resistance parameters by using elastic plastic finite element analysis. For the given geometry of the specimen analyzed, the governing parameter of elastic plastic crack tip stress field IN integral and the stress triaxiality parameter G integral and plastic stress intensity factor were determined as a function of mode mixity and elastic plastic material properties. The numerical results of the specimen geometries considered indicated coupling between mode mixity and material nonlinearity. A significant effect of elastic plastic material properties described by strain hardening exponent on G integral is observed in the full range of mode mixity. It is demonstrated that in plane strain and full 3D problems, the plastic stress intensity factor can be used as a general one-term parameter to characterize the fracture resistance for a variety of specimen configurations and different mixed mode loadings. Thank you very much for your attention.
Thank you for your presentation. We have time for 1-2 minutes if you want to questions.